Okay, have you ever, really stopped to think about the stuff around us? Where it comes from, how it's made, and critically, where it goes when we're done with it. It's this whole hidden journey, isn't it? From deep in the earth through all these processes right up until it's, well, discarded. Today, we're doing a deep dive into exactly that, environmental and societal issues in materials, science, and engineering. And we're using Chapter 22 of Callister and Rethwish's Materials, Science, and Engineering, an introduction as our guide, our mission. To walk you through the big questions engineers grapple with stuff about the environment, resources, society. We'll break down the key ideas, definitions, examples, all audio, no visuals needed.
Yeah, and it's so important because we're shifting focus. It's not just about is this material strong enough or does it conduct electricity well?
Yeah.
It's about the bigger picture, the impact our choices have on the planet, on people now, and, well, down the line. It's vital for engineers, definitely, but honestly, for anyone using anything.
Exactly. It's about the whole story of a material, not just its job description. So let's get into that life cycle. We hear terms like cradle-to-grave thrown around, but what does that really look like for, say, a plastic bottle or a metal component? The chapter calls this the total material cycle. It's like the foundational map for understanding environmental impact.
It really is. Try to picture this maybe like a big circle or loop. You start way over on the left with raw materials, could be ore from a mine, trees, oil, whatever. Then arrows show it moving to extraction, production, and processing. That's digging it up, refining it, getting it into a basic, usable form.
Okay, raw materials, then processing.
Right. Then it becomes engineered materials. This is where you get specific stuff like steel alloys or ceramics or different kinds of plastics. From there, it flows into product design, manufacture, assembly, shaping, treating, putting things together into the items we actually buy and use.
Got it. So the phone in my hand or the chair I'm sitting on.
Exactly. That's the next stage. Applications. You're using the product until, it breaks or you upgrade or whatever. And then comes the big fork in the road. Does it go to recycle or reuse, looping back into the system? Or does it become waste, heading for disposal, maybe landfill, and kind of completing the cycle by returning to the earth, but not necessarily in a good way?
That visual helps a lot.
Yeah.
It really shows the potential for, well, leakage, right? Where things fall out of that ideal loop.
Precisely. And the scale is, frankly, enormous. The book mentions something like 15 billion tons of raw materials are extracted globally every single year. 15 billion.
Wow.
Yeah. And when you remember that Earth is, for the most part, a closed system, resources-wise, it really makes you think these materials aren't infinite.
And it's not just the materials themselves, it's the energy, right? I saw a stat in there that blew me away.
Oh, the manufacturing energy.
Yeah. Roughly half the energy used by U.S. manufacturing industries goes just into producing and fabricating the materials before they even become a finished product.
Yeah. It's staggering, isn't it? And that energy use has its own environmental baggage, of course. But the key point, and the chapter stresses this, is that environmental impacts pop up all along that cycle. It's not just the landfill at the end.
Right.
You've got ecological damage from, say, mining. You've got pollutants from processing plants. And then you have the disposal challenge. Every single step matters.
So thinking about that whole chain, it makes recycling look less like a nice to do and more like a necessity.
Absolutely critical. The chapter lays out several powerful reasons why.
Okay, what are the big ones?
Well, first, it obviously conserves natural resources. If you reuse aluminum, you don't need to mine as much bauxite ore. Less mining, less ecological disruption.
Makes sense.
Second, the energy savers can be massive. We talked about that aluminum example. It takes something like 28 times more energy to make aluminum from raw ore versus recycling scrap. Just think about that.
28 times.
Yeah, huge difference. And third, it directly reduces the amount of stuff going into landfills or incinerators. It tackles the disposal problem head on.
Okay, with benefits like that, it's no wonder industries are looking seriously at things like life cycle analysis, LCA, and green design. How do those work in practice?
So LCA, life cycle analysis, it's basically a systematic accounting process. Think of figure 22.2 from the chapter. It shows NMPTS on one side, energy, raw materials going in. These inputs flow through all the life stages: materials production, product manufacturing, product use, product disposal. And on the other side, you meticulously track the output. That includes the usable product itself, sure, but also everything else: water effluents, air emissions, solid waste, any other environmental impacts.
So it's like a full environmental balance sheet for a product's entire life.
Exactly, quantifying everything. And that ties directly into green design, which is about using that LCA information proactively to make more environmentally sound choices right from the start.
Which brings us to sustainability. It's used everywhere, but here it means something specific, doesn't it?
It does. It's about finding a way to live well now and ensuring future generations can too, without wrecking the environment in the process. It means using resources wisely at a rate they can be replenished and keeping pollution below levels the planet can handle.
Is that where standards like ISO 14001 come in?
Yep. ISO 14001 gives organizations a framework. It helps them manage their environmental responsibilities, comply with laws, but also find that balance between being profitable and being, well, green. It pushes for that proactive thinking.
Okay, so if sustainability is the aim, the chapter suggests materials should ideally be one of two things: completely recyclable or completely biodegradable. Let's unpack those terms. What's the real difference?
Good question. Recyclable basically means you can take the used material, reprocess it, and make new stuff out of it, potentially over and over, without the quality dropping too much. Think like glass bottles becoming new glass bottles.
Right.
Completely biodegradable, though, means the material breaks down naturally. Microorganisms, sunlight, water. They eventually return it to its basic natural components, like those special compostable bags for leaves.
Okay, clear distinction. Now, recycling sounds great, but we all know that bin, with mixed paper, plastic, metal, separating it is tough, especially for complex things like cars. How do they take apart a scrapped car efficiently?
Yeah, a car is a real mix master. But the industry's gotten pretty clever. First, they often use these massive shredders, hammer mills that can just pulverize a car into fist-sized chunks in, like, under 20 seconds.
Bro.
Yeah, it's intense. Then the sorting begins. Steel and other iron-based alloys. Easy pickings for powerful magnets. That's magnetic separation.
Okay, that handles the ferrous stuff. What about aluminum, copper?
That's where eddy current separators come in. It's neat physics. They use strong, rapidly changing magnetic fields. These fields induce electrical currents, eddy currents, within the non-ferrous metal pieces, like aluminum or copper. These induced currents create their own temporary magnetic fields that oppose the main field. It's like trying to push the north poles of two magnets together. They repel. So the machine literally flings the non-ferrous metals off the conveyor belt.
Wow, okay, that's clever, like a magnetic ejector seat for aluminum.
Kind of, yeah. Then you might have something called a gravity table. Picture an inclined table that vibrates and has air blowing up through it. Lighter materials like plastics or foams get sort of floated and pushed one way by the air, while heavier stuff, maybe glass fragments or remaining metals, gets vibrated down a different path. It separates based on density and aerodynamics.
Amazing technologies. So we have the big picture, the sorting. Let's dive into specific materials. Metals. You mentioned they have a kind of mixed environmental record.
They really do. On one hand, many common metals, like iron, will eventually rust and corrode. It's a form of biodegradation, returning them to mineral states. But it can take a very long time. And then you have metals like lead, mercury, cadmium, highly toxic. Their disposal is a major concern.
And recycling them isn't always straightforward either.
Right. While lots of alloys are recyclable, often the quality degrades slightly each time. It gets downcycled into less demanding applications. Plus, how the product was originally made matters hugely.
How so?
Well, if you weld two different types of aluminum alloys together or use certain coatings or embed fasteners, it can make separating and recycling much harder or even impossible without contamination. Design for disassembly is key.
But you mentioned aluminum specifically as a success story, despite being pretty non-biodegradable because it resists corrosion so well.
Absolutely. It's highly recyclable, and that energy saving 28 times less energy, remember, is primarily associated with aluminum. It's a massive win.
Where does most recycled aluminum come from?
Huge amounts come from used beverage cans, obviously, but also scrapped cars, building materials, airplanes. It's widely recovered.
Okay, let's switch gears to glass. You hear about it clogging up landfills because it just sits there, doesn't really break down.
That's true. It's very inert, non-biodegradable. But the flip side is incredible. The chapter calls glass an ideal recyclable material.
Ideal? Why?
Because you can melt it down and reform it into new high-quality glass products again and again with basically no loss in quality. It doesn't get downcycled like some metals or plastics might.
That is a huge plus. What's the recycling process like?
First, it needs careful sorting. By color, clear, amber, green, because mixed colors make off-color glass, and sometimes by composition separating standard soda lime glass from, say, borosilicate glass like Pyrex or leaded crystal,
Okay, sorting first.
then washing to remove labels and residues. Then it's crushed into small fragments called cullet. That cullet is the raw material. It can be melted directly to make new containers, or it can be used in other ways too, as aggregate in concrete or asphalt, in fiberglass insulations, sometimes in decorative countertops, even as abrasives or to help bricks melt better during firing. Lots of uses.
All right, now for the big one. Plastics and rubbers. Their durability is a blessing and a curse, isn't it? Most are super resistant to degradation.
Exactly. That inertness means they stick around for a long, long time. Packaging, old cars, especially tires, they create massive waste disposal headaches.
Can't we just burn them?
Some can be incinerated for energy, but many release toxic gases if not burned under very controlled high-temperature conditions. And while there are biodegradable plastics, they've historically been more expensive or had performance limitations, though that's changing.
Let's focus on the common thermoplastics first. Those are the ones that soften when heated, right? That
Yeah.
makes them easier to recycle.
Generally, yes, because you can melt and reshape them. Sorting is still key, though. After shredding and washing, they use things like photoelectric sensors to sort by color. And for sorting by plastic type, flotation tanks are common. Different plastics have different densities, so some float and some sink in water or other liquids, allowing separation.
And those little numbers and triangles on the bottom of the containers.
Ah, yes, the resin identification codes. Numbers 1 through 7. They tell recyclers what type of plastic it is. You probably recognize them. For example, number 1 is PT, polyethylene terephthalate. Think soft drink bottles. Recycled PD can become things like carpet fibers, industrial strapping, sometimes even fabric for clothes.
Okay, and like number 2.
That's HDPE, high-density polyethylene. Milk jugs, detergent bottles. That often gets recycled into things like plastic lumber, drainage pipes, or maybe those durable plastic cutting boards.
But even with thermoplastics, there's still that downcycling issue sometimes.
Often, yeah. Recycled plastic might not have quite the same pristine properties as virgin plastic, so it often goes into applications that are a bit less demanding. It's usually cheaper, though.
Now, rubbers.
Yeah.
Tires seem like the biggest challenge there. They're tough, non-biodegradable, bulky.
And they float in landfills, which is a problem. And tire fires are notoriously nasty and hard to put out. It's a huge volume issue.
So what do we do with millions of old tires?
Actually, a surprisingly high percentage are recycled now. The process usually starts with shredding them into chips, maybe around 20 millimeters. Then, magnetic separation pulls out the steel reinforcing wire that gets sold as scrap metal. The rubber chips are then ground down further into what's called crumb rubber. These can be tiny particles, sometimes less than a millimeter across.
Crumb rubber, what's that used for?
Oh, lots of things. A big one is rubberized asphalt for roads. It makes the pavement quieter, last longer, and it uses up tons of old tires.
I've heard of that.
Yeah. Also, those soft, bouncy surfaces you find on playgrounds and athletic tracks. Often made from crumb rubber. Landscaping mulch, too. Even things like flip-flops. And it can be burned as fuel in controlled environments, like cement kilns.
Any alternatives for new products?
Yes, there's a class called thermoplastic elastomers, or TPEs. They behave like rubber but can be processed like thermoplastics melted and reformed, making them easier to recycle than traditional vulcanized rubber.
Okay, another complex category, composite materials.
Mhm.
Things like fiberglass or carbon fiber reinforced plastics. Why are they so tough to recycle?
It's inherent in their nature, really. They're made by combining very different materials, like strong fibers and a polymer matrix, often mixed very intimately at a microscopic level. Taking them apart cleanly is, well, difficult.
But there are ways.
There are approaches being developed and used, mainly for those polymer matrix composites. The chapter outlines 3 main types. First is mechanical recycling, basically grinding the whole composite down into small particles or powders. These can then be used as fillers or maybe low-grade reinforcement in other materials like concrete or plastics.
Okay, grinding it up. What else?
Second is thermal recycling. Using heat, you essentially burn off or vaporize the polymer matrix, leaving the reinforcing fibers behind glass or carbon.
Do the fibers survive? Okay.
They can be damaged or shortened by the heat, so their properties might be reduced. But you recover the valuable fibers, and you can also capture the heat energy released from burning the polymer.
And the third way?
Chemical recycling. This uses solvents or chemical reactions to dissolve or break down the polymer matrix, separating it from the fibers. The main goal here is usually high-quality fiber recovery.
Are these recycled composite materials finding uses?
They are, yes. Recycled fiberglass shows up in things like artificial lumber for decking, sometimes mixed into concrete or asphalt, even decorative panels. Recycled carbon fiber is finding niche uses in things like shielding against electromagnetic interference, in anti-static paints, or for lightweight automotive parts where maybe the absolute highest performance isn't needed.
Thinking about tricky waste streams, we have to talk about electronic waste. E-waste. It feels like a tidal wave these days.
It really is. All our old computers, phones, TVs, printers. The turnover is so fast, and the volume is just immense. It's a huge, growing category of waste.
And it's not just bulky, it's often hazardous, right?
Exactly. E-waste is a complex mix. It contains valuable, non-hazardous materials. We definitely want to recover copper, gold, silver, aluminum, plastics. But it also contains hazardous stuff. Lead, like in old CRT monitors, cadmium in batteries, mercury in switches and lamps, those brominated flame retardants used in plastic casings and circuit boards, these are seriously toxic if they leach into the environment.
Which makes proper recycling crucial. But I've heard that, well, a lot of it doesn't get recycled properly.
That's unfortunately true, and a major issue highlighted in the chapter. A significant amount of e-waste, particularly from developed nations, ends up being exported, often to developing countries. There, the recycling methods can be really primitive and dangerous. People manually dismantling components, burning cables in open fires to get copper, using strong acids in open pits to leach out precious metals.
That sounds incredibly dangerous.
It is. It leads to severe health problems for the workers, often including children, and widespread contamination of soil, water, and air. It's a serious global environmental justice issue.
Wow. Okay, so that's a pretty sobering picture for some materials. But the chapter does end on a more hopeful note, looking at solutions, particularly for polymers, biodegradable and biorenewable plastics.
Yes, exactly. Faced with the problems of plastics piling up in landfills and oceans, there's been a real push to develop better alternatives.
It wasn't always smooth sailing, though.
No, back in the 70s and 80s, there was this initial panic about landfills filling up. Some early degradable plastics were introduced, but frankly, they often didn't work very well or degraded incompletely, which kind of gave the whole concept a bad name for a while.
But things have improved.
Definitely. We now have much better standards for actually measuring biodegradability, and that spurred the development of a new generation of polymers that really do break down under specific conditions. They're finding good uses, especially in niche areas, like those compostable bags for yard waste. You can just toss the whole bag in the compost pile.
Right.
And a really interesting one is biodegradable mulch films for agriculture. Farmers often use plastic sheets to cover soil, control weeds, warm the ground, but collecting and disposing of traditional polyethylene film is a huge hassle.
I can imagine.
So now they have biodegradable films, maybe made from starch-based polymers or PLA blends that they can just plow directly into the soil after the harvest. The microbes break it down, enriching the soil. Figure 22.3 in the text shows this kind of application.
That seems like a perfect application. Any others?
Potential in food service disposable cutlery containers is definitely being explored. And then there's the whole area of biorenewable polymers. These aren't just biodegradable. Their starting materials come from renewable resources, like plants, instead of fossil fuels.
Reducing oil dependence and greenhouse gases.
That's the goal, yes. Biomass, like corn or sugarcane, becomes the feedstock.
And the prime example here seems to be polylactic acid, or PLA.
PLA is definitely a star player right now. It's derived from lactic acid, which can be produced by fermenting sugars from corn, sugar beets, wheat, renewable sources.
What's its structure like? Can you describe it?
Sure. Chemically, it's a repeat unit. Imagine a chain. Each link has a carbon atom double bonded to an oxygen. Then that's single bonded to another oxygen atom. That oxygen links to a carbon atom, which has a hydrogen and a methyl group, a CH3 attached. Then that carbon links to another carbon, which is double bonded to an oxygen. And finally, an oxygen atom that connects to the start of the next repeat unit. It's a polyester.
Okay, got the picture. And its properties, how does it stack up?
Pretty well, actually. Its mechanical properties are quite similar to peat, that common plastic in drink bottles. This is huge because it means PLA can often be processed using existing equipment designed for traditional plastics. It's typically transparent, has good resistance to moisture and grease, doesn't hold odors, great for packaging.
Any other unique features?
Yes, a really interesting one is that it's bioresorbable. That means it can safely break down and be absorbed by the human body over time.
Ah, so medical uses.
Exactly. It's used for things like dissolvable sutures, screws, and plates for bone fixation, drug delivery systems. places where you want the material to do its job and then just gradually disappear.
And how does it biodegrade in the environment? Is it like those early plastics?
No, it's much more specific. PLA is quite stable at room temperature. It doesn't just crumble on the shelf. It needs the conditions found in industrial composting facilities, basically, elevated temperatures, around 60 degrees C or 140 degrees F, and moisture with the right microbes present. Degradation happens in two stages. First, water breaks down the long polymer chains, that's hydrolytic cleavage. Then, microorganisms consume the smaller lactic acid fragments.
So it won't just disappear in your cupboard, but it will break down properly in a composter. Is it recyclable too?
Yes, it can be. It can be chemically recycled back to lactic acid, its monomer, which can then be used to make new virgin PLA.
Seems very versatile.
Hmm.
Any other applications?
Textiles are a growing area. PLA fibers have good crimp retention, like wool. They resist UV light well, and they're relatively non-flammable compared to some synthetics. So you might find it in upholstery, drapes, carpets, even disposable fabrics like in diapers. The big hurdle, as with many new materials, was initially the cost. Making PLA used to be quite expensive compared to petroleum-based plastics.
But that's improving.
Significantly. More efficient production methods and larger-scale manufacturing are bringing the cost down, making it much more competitive.
So wrapping this all up, what's the big takeaway for someone listening, maybe someone studying engineering or just interested in how the world works? It really seems like every single material choice we make, or engineers make, sends ripples out across the environment and society. We've journeyed through that whole materials cycle, seen why LCA and green design are so vital, navigated the tricky realities of recycling different metals, glass, plastics, composites, e-waste, and looked at promising future paths like PLA. The underlying message seems to be that material science isn't just about performance anymore. It's about responsibility, stewardship.
I think that's exactly right. Understanding these environmental and societal aspects, it's not just about meeting regulations or being green for marketing. It's fundamental to being a good engineer, an ethical innovator. How can we design things better, choose materials more wisely, plan for the end of life right from the beginning to create a genuinely more sustainable future? That's the real challenge.
So here's a final thought for you to ponder as you go about your day. Look at the objects around you. Which material, maybe one we use every day without thinking, do you think is poised for the next big shift? Which one might move from being seen mostly as waste at the end of its life to becoming part of a truly sustainable, maybe even circular story? Something to think about. Thank you so much for joining us on this deep dive today.